Swayam Prabha. Digital India. Educated India.
Okay, so let us continue with this proof of the classification theorem for plane curves. And as I already told you, you cannot deduce it from the classification theorem for space curves. Okay, so the first step is that you have to show that you take a curve and move it by a rigid motion. Okay, then the original curve and the new curve, they both have the same signed curvature. Okay, and as I told you, the important thing is that the signed curvature is it was defined geometrically, but it is described analytically as the rate of change of a turning angle, and that turning angle concept has to be used. Okay, and mind you, there is no such concept when you look at space curves. Okay, so let me start with the following thing. Suppose gamma is a unit speed parameterized plane curve. Okay, so we start with gamma, a unit speed parameterized plane curve. So gamma is gamma of s. Okay, s is varying in open interval AB on the real line. Okay, and s is arc length. S is arc length. Okay, and m from R2 to R2 you see is a rigid motion. Rigid motion of R2, so that is very important. All right, so what does it mean? It means m is a it is an isometry, and it is a direct isometry, or it's an orientation preserving isometry. Okay, and remember that you see orientation preserving means that it will not only preserve the angles between vectors, but it will also preserve the sense of that in which the angles are taken. Okay, so let me let me take such an m, and then the point is that if you move gamma by m, you get a new curve, and it's a new plane curve, and the fact is that this m circle gamma also has the same sign curvature as gamma. Okay, then the sign curvatures of gamma and of m circle gamma are the same. Okay, so what this basically says is that the sign curvature depends only on the rigid motion equivalence class of a plane curve. Okay, so what does this mean? That is k signed of gamma of s is the same as k signed of m circle gamma of s. Okay, now how does how do you prove this statement? So you see, you have so remember that so you see the if you take so for gamma s, okay, how do you get the sign curvature? So the way this is done is that you have to use the fact that the sign curvature is the derivative with respect to the arc length of a turning angle, and for that you need to use the fact that every c1 vector, every c1 unit vector admits a turning angle. Okay, so for gamma s, you see gamma dot s, norm gamma dot s is 1. Okay, since gamma is unit speed. Okay, since gamma s is unit speed. Okay. So and gamma you take to be in C2AB, okay, it's twice continuously differentiable, all right. So this implies that gamma dot s is first continuously differentiable in AB, okay. Mind you, to talk about curvature you need the second derivative, and we follow the rule that whenever you talk of a derivative you also assume it's continuous. So curvature is essentially the second derivative, all right. For a unit speed curve, if you take the magnitude of the acceleration, that's your curvature, okay, at least in magnitude, okay. So so gamma has to be twice continuously differentiable, which means up to the second derivative of gamma should exist and it must be continuous. And then this means that the first derivative of gamma with respect to s is first continuously differentiable, and then this means that your gamma dot is a first continuously differentiable unit vector, and we know that for a first continuously differentiable unit vector there is a turning angle, okay. So there exists a turning angle phi gamma of s for gamma of s, that is d phi gamma of s by ds is ks gamma of s. So the rate of change of the turning angle is your sine curvature, and of course turning angle for so I should say there is a turning angle for gamma dot, okay. So that's important. The turning angle is for a C1 unit vector, okay. So there is a turning angle for gamma dot, and the rate of change of the turning angle is the sine curvature, okay. That is a correct analytic description of the sine curvature, okay. And of course you can write gamma dot s as how is gamma dot related to the turning angle? It is cos of the turning angle comma sine of the turning angle, okay. And the idea is that if this is your curve gamma and you have this point which is gamma s, then you see this unit vector here is going to be gamma dot s, okay. And this with respect to some fixed direction, let us say positive x direction, so positive x direction, the turning angle is measured like this. So phi sub gamma of s is measured like this. So it is measured with sense from a fixed direction to rotate towards the the unit tangent vector, okay. And this should be measured in the anticlockwise sense, all right. So then gamma dot can be written as cos phi gamma s sin phi gamma s, okay. The whole point about all this is that you see, after all, if you take any unit vector you can always write it as cos theta sin theta, that's not a big deal. But the point is, if the unit vector is C1, then the theta can also be made C1, and that is always tricky because usually the angle function itself is discontinuous around a point. So that's where there is a little bit of technicality here, right. So we have this very important for the plane curve case, and it's only from this description that you get the Frenet-Serret. So the Frenet-Serret for gamma will be d by ds of here I have to write t cap gamma of s ns cap sub gamma of s is equal to 0 ks sub gamma of s and then here I have to put negative of that minus ks sub gamma of s 0, and on this side you are going to get t cap gamma of s ns cap sub gamma of s, okay. So this is the Frenet-Serret differential equation, okay. And of course here t cap sub gamma of s is just nothing but d by ds of gamma of s, and this is just gamma dot of s. So this is the unit tangent vector. And how is the what is ns cap is subscript gamma s is actually the it is the sine normal So it is obtained from the unit tangent vector by rotating it by 90 degrees in the anticlockwise sense. So so what you do is that so in this picture, suppose I draw it here. So this vector is gamma dot of s, okay, and this is just t cap sub gamma of s, okay, and then you rotate it 90 degrees like this, okay, and you get ns sub gamma cap, okay. So you get the sign normal, right? And so then you have these Frenet-Serret relations, okay, and everything is dependent on the Stirling angle. That's what I want you to understand. All right. Now you see, if you calculate, so now we have to look at what happens when you apply this rigid motion m to gamma, okay. Then the first thing is that if you apply the rigid motion m to gamma, you are still getting a unit speed curve parameterized by s, okay. So you see, if you calculate, so I should say, yeah. So if we consider m circle gamma of s, all right, then you see, so here is something that I need to do. You see, this m from R2 to R2 is a rigid motion, okay. We already know that we have done this for general Rn, that whenever you have rigid motion, you can write it as a linear isometry followed by a translation in a unique way. So that also applies here. So then then your m is actually translation by m0, a composition g sub m, okay, where g sub m is just m minus m0, okay, and this g sub m is a linear oriented isometry of R2, okay. And again, it is as we have already seen, you see, for an isometry to be linear, it is enough that it takes 0 to 0, and then it will preserve dot products, it will preserve norms, okay. And also there are only two things it can do. It can either preserve the orientation or it can reverse the orientation, okay. And the orientation will be preserved if the matrix of that linear isometry has determinant +1, okay. Otherwise it will have determinant -1 and it will reverse the orientation, okay. And so in this case, what will happen is that matrix of Gm has determinant equal to 1, okay. You will have this, right. And so you see, if you calculate d by ds of m circle gamma of s, okay, it will be d by ds of m of gamma of s, okay. And if you look at it, let's calculate d by ds of m circle gamma s. It is d by ds of m of gamma of s, but you see m is just tm0 circle gm. So this is actually so if you look at it, this m is gm plus m0, so it is just d by ds of g of gamma of s plus m of 0, okay. M of 0 is a constant vector, all right. Mind you, m is just a rigid motion, it need not preserve the origin. So you get origin will move to another point m0, okay, and that is a translation by m0 which is coming here in the decomposition of m, okay. So but of course m0 is a constant vector, d by ds when you apply it will go away, so I will simply get d by ds of g of gamma of s, okay. And this is, mind you, G is a constant matrix, okay. G is represented by a matrix. If you think gamma of s to be represented by a column vector, okay, then G is represented by a constant matrix, and since G is a constant matrix, G will come out. Okay, if you think of it as matrix 2 by 2 matrix acting on a 2 by 2 2 by 1 column vector. Okay, so this will be G into d by ds of gamma of s, and that is G gamma dot of s. Okay, so what you get is that you are getting m circle gamma whole dot of s is G of gamma dot of s. Okay, and if you calculate norm of m circle gamma whole dot of s, okay, this will therefore be norm of G of gamma dot of s. Okay, and you see G is an isometry and is a linear isometry, so G preserves norms. So norm of G of V is the same as norm V. Okay, therefore this is the same as norm of gamma dot of s. Okay, and this step is because since G is a linear isometry, G preserves norms. Okay, so you will get so the G goes away, I will get norm gamma dot, and this is going to be 1 because gamma dot gamma is unit speed. So what this tells you is that this calculation tells you if you take m circle gamma dot, that is also norm 1, therefore m circle gamma is also unit speed parameterized. Okay, so this implies that m circle gamma is also unit speed parameterized. Okay, then so you can talk about its sign curvature. Okay, so what you do is that you have to look at so I have to say so you see yeah, so you again look at this equation, so you get m circle gamma. So let me do the following thing, I will put m circle gamma as gamma 1, so put gamma 1 is equal to m circle gamma, so that you can avoid writing m circle gamma many times. Okay, so this first equation becomes gamma 1 dot, okay, of s is equal to G gamma dot of s, you are getting this. Okay, and but you see your gamma dot is a C1 unit vector, so it has a turning angle, all right, and the rate of change of that turning angle is exactly the sign curvature of gamma dot. Okay, and similarly gamma 1 dot is also a unit speed vector. Okay, it's a unit vector C1, it's a C1 unit vector. Okay, it will also have a turning angle, all right, and the derivative of that turning angle with respect to s will give you the sign curvature of gamma 1. Okay, and you have to conclude from this that the sign curvatures are the same. So how does one do that? So you see, let me say the following thing. So you have so this gamma 1 dot of s is actually T cap gamma 1 of s. Okay, by definition T cap is just gamma dot. Okay, and this guy here is G T cap gamma of s. Okay, so that's what you are getting. All right, now differentiate one more time. Okay, because I would like to use the first Frenet-Serret relation that T cap dot is ks into n s cap. I would like to use this first Frenet-Serret relation. So you differentiate once more, you apply d by ds to this, you will get T cap dot gamma 1 of s is equal to, if I do d by ds on the right side, G is a constant. Okay, if you think of it as a matrix, it will come out. So I will get G into derivative inside is going to be T cap dot of gamma of s. Okay, and now apply the Frenet-Serret. You will get ns sub gamma 1 cap of s times, so in fact let me write the scalar on the left, the scalar is the sign curvature, so I should write ks sub gamma 1 of S times ns sub gamma 1 of S cap, okay, that is equal to Ks sub gamma of S on the right side, and there is a G here outside, let me not forget that, and I will have a ns hat gamma of S, okay. So this is what I will get, okay. So this is by the Frenet-Serret, okay. Now you see G is a linear map, and in a linear map scalars can be pulled out of the argument, okay. So this Ks Ks sub gamma of S is actually a scalar. So this ns hat is the vector part and the Ks is the scalar part, and in a linear map you can pull out the scalars from the argument of the map. So what I can do is essentially I can so I will get this is also equal to, I pull out this Ks sub gamma of S out, and I will get G ns cap sub gamma of S, okay. That is, this is since G is a linear map and Ks sub gamma of S is a scalar, all right. So on one side I have Ks sub gamma 1 of S into ns sub gamma 1 cap of S, okay, is equal to, on the other side I have Ks gamma S times G times ns cap gamma of S, okay. Now to show that this Ks gamma 1 S, which is the sine curvature of the new curve, is the same as the sine curvature of the old curve, I just have to show that the new signed normal is G operating on the older sine normal, but that is obvious because G is G is oriented. So you see look at this, you have gamma, okay, you have this point, so at this point you have gamma dot of S, which is, mind you, it is T cap sub gamma of S, okay, and then you rotate it by 90 degrees in the anticlockwise sense and you get ns cap sub gamma of S, okay. Now what you do is you are applying this rigid motion M, okay. When you apply this rigid motion M, what happens is that you get basically the way you apply this rigid motion is basically this, it is a first you can think of it as a translation followed by a rotation, or a rotation followed by a translation, okay, whichever way you want it. But essentially what is going to happen is that you are going to get a curve like this, okay, and this is your M circle gamma of S, which is gamma 1 S, okay, and this point is going to go to this some point here, all right, and this gamma dot will go to here, it will go to gamma so what I have got for the new curve, you see I have got so here I will get so I should say the following thing, so I have gamma dot, and this gamma 1 dot, okay, is actually G gamma, all right, and this is also M gamma, okay. So let me write that correctly, gamma 1 dot is G gamma dot is equal to is also equal to M gamma dot, okay. So why is this? You see so M has a translation, I want to say translation will not, so I should, let me write this correctly. So it's M gamma whole dot. So this is equal to M gamma the whole dot, okay. See, the point is that when you take the dot, the translation part in M is gone, okay. When you do d by ds, the translation by a constant vector, that vanishes. So the only effect is left of what is remaining, which is the rotation, which is G. So you see it is just G of gamma dot, okay. So that we have already that is already here. For the new curve, the gamma 1 dot is g of the original gamma dot of the original curve, all right. And look at applying g to this, okay. If you apply g to this, I claim that you will get the sign normal of gamma 1. Why? Because you see this gamma dot, that is t cap gamma and ns cap gamma, they form an orthonormal set of vectors taken in the positive sense, okay. So when you apply g to them, again you will get an orthonormal set of vectors with the sense of the angle being preserved. That means that you see, if you apply g to ns cap gamma of s, you will get ns cap gamma 1. That is because g will take ns cap gamma of s to exactly the gamma 1 dot rotated counterclockwise 90 degrees by I mean gamma 1 dot rotated counterclockwise by 90 degrees, and that is actually ns gamma 1. See, by definition, I hope this is clear. You see, this gamma 1 dot is actually t cap gamma 1, all right, and this, if you rotate it counterclockwise by 90 degrees, you are supposed to get ns cap gamma 1, okay. But you see, if you take the original gamma dot, which is the original t cap and the original n cap, and you apply g to both, the new, when you apply g to the t cap, you get gamma 1 dot, which is the t cap of gamma 1, okay. And when you apply g to ns cap, you should again get a vector perpendicular to t cap gamma 1, and it should also preserve the sense. So it has to be ns cap gamma 1. That's what I want you to understand. So I am just saying that, if you look at it, these two guys are actually equal. They are the same. The reason is because g maps orthogonal vectors to orthogonal vectors, and it also preserves the sense between the sense of the angle between the two vectors. It maps orthogonal vectors to orthogonal vectors, okay. But even the sense in which you measure that 90 degree angle, even that sense is preserved because it's an oriented isometry. Therefore, you see this ns cap gamma 1 is g ns cap gamma. So these two vectors are the same, and therefore these two scalars are the same. That's what I want you to understand. If two vectors are the same and they are multiplied by scalars and they are equal, then the scalar part will be the same. And to check that, you have to only dot with the vector on both sides, the equal vector on both sides, okay. So here I am using the fact that g is an oriented isometry, okay, and which is also linear. I am using that, okay. So hence let me write this. G takes the orthonormal set t cap gamma of s, ns cap sub gamma of s to g t cap gamma of s, which is t cap gamma 1 s comma g ns cap sub gamma of s, okay. And the angle from t cap gamma of s to ns cap sub gamma of s is 90 degrees anti-clockwise and g oriented. G will in fact it is easy to check that such a g will be a rotation, okay, and g oriented will imply that the angle from g of t cap gamma of s, which is t gamma 1 cap of s, to G ns cap sub gamma of s is 90 degrees anticlockwise. Okay. But if you take t cap gamma 1 and rotate it anticlockwise in 90 degrees, you will only get the ns cap for gamma 1, you will get the sine normal of gamma 1. So this implies that G ns cap sub gamma of s is actually ns sub cap of gamma 1 of s. Okay, and this implies that k, so from this equation, if I call this equation as star, okay, from star you see these two vectors are equal, therefore the coefficients are equal. Okay, therefore star implies that the sine curvature of gamma 1 of s is the same as the sine curvature of gamma of s, and of course gamma 1 is just m circle gamma. This is just sine curvature of okay. So therefore you see you have that if you move a curve by a rigid motion, then the sine curvatures are the same. Okay, and somehow in this argument so far I have not used the turning angle. Okay, but it will come up, maybe it will come up in trying to prove the other relations. But indirectly you must understand that the turning angle is involved because the sine curvature is involved. Okay, so it is indirectly involved. So so we have proved that if you have two curves, if you take a curve and move it by rigid motion, then the sine curvatures are the same. Okay, now we want to show that if you have so you have to prove two more statements. If two curves have the same sine curvature, okay, then you have to show that one can be moved to the other by a rigid motion. You have to do that, all right. And the other thing that you have to prove is that if you give me any continuous function, okay, then I can find a curve for which that continuous function is the sine curvature. Okay, so these are two more statements that need to be proved, and so let us prove those statements. So the next thing is next we suppose that gamma 1 and gamma 2 are two unit speed parametrized curves such that the sine curvatures are the same. We show that there exists a rigid motion m of R2 such that gamma 2 is m circle gamma 1. Okay, so if two curves have the same sine curvature, then they differ by a rigid motion. Okay, so this and the previous statement that if you change a curve by a rigid motion, then the sine curvature is the same, that along with this statement actually what it shows is that the mapping that takes the equivalence class, the rigid motion equivalence class of a curve into the sine curvature is injective. Okay, two rigid motion equivalence classes of two curves with the same sine curvature functions, they are rigid motion equivalent to one another. That means the rigid motion equivalence classes are equal. Okay, that's what it means. All right. So so how does one prove this? So perhaps here we will use the the interpretation of the sine curvature as rate of change of the turning angle. Okay, so so you have gamma 1, you have for this you have gamma 1 dot. Okay, and this is a C1 unit vector. So therefore it has a turning angle So this implies that there exists a turning angle. Let me call it as phi sub gamma 1 of s, okay, and you will have gamma 1 dot of s to be, you know, cosine and sine of this turning angle. Okay, and you will also have that the rate of change of the turning angle is the sine curvature. So d phi gamma 1 s by ds is equal to k sine gamma 1 of s. Okay, and similarly you will have the same kind of thing for the second curve. Gamma 2 gives rise to gamma 2 dot, and that is also going to be a C1 unit vector. So it will have a turning angle. And that will be phi gamma 2 of s. Okay, and again you will get that gamma 2 dot of s is cosine of phi sub gamma 2 of s, sine of phi sub gamma 2 of s, and d phi gamma 2s by ds is actually ks sub gamma 2 of s. Okay, so you have this for both the curves, and what is given is that these two are equal. So these two are given equal. Okay, and so the what is given is that you are given two curves for which the sine curvatures are equal. Okay, and the sine curvatures are the rates of change of the corresponding, you know, turning angles. So now you have to so this derivative and this derivative are equal. That means they differ by a constant. Okay, so d phi 1 d phi gamma 1 s by ds is equal to d phi gamma 2 s by ds, and this implies that, you know, phi gamma 2 of s is equal to phi gamma 1 of phi gamma 2 of let me put this on top. Phi gamma 2 of s is equal to phi gamma 1 of s plus some phi naught. Okay, so so now from this you want to say that gamma 2 is rigid motion times gamma 1. Okay, but how do you get gamma 2? You can get gamma 2 by integrating gamma 2 dot. Okay, and how do you connect gamma 2 dot with the turning angle? Gamma 2 dot is cos phi gamma 2 sin phi gamma 2. Okay, so that's the way we have to go. So gamma 2 of s, okay, minus gamma 2 of s naught is equal to integral s naught to s. So for some s naught point in you know, fixed point, for some, you know, you take some s naught in AB. Okay, then by the fundamental theorem of calculus, gamma 2s minus gamma 2 s naught is integral s naught to s gamma 2 dot of s ds. Okay, but you see this is integral from s naught to s. Gamma 2 dot of s is nothing but you know, gamma 2 dot of s is here by the turning angle. It is just cos phi gamma 2 sin phi gamma 2. So I will get cos phi gamma 2 of s comma sin phi gamma sub gamma 2 of s ds. Okay, so you see I am integrating a vector. Okay, and what it means is that you integrate every component, right? So this means that this is the same as, you see, but you also use this fact that phi gamma 2 of s is phi gamma 1 s plus phi naught, because that is your you know that comes from the fact that the sine curvatures are the same. All right, so if you plug in that, you will get s naught to s cos of phi gamma 1 of s plus phi naught, you know, sine of phi gamma 1 s plus phi naught, you know, ds. Okay, and what is this? So you see you use the cosine of sum of angles formula. So this is going to be integral s naught to s. I will get cos phi gamma 1 s cos phi naught minus sine phi gamma 1 s sine phi naught in the first component. The second component I will get sine phi gamma 1 of s cos phi naught plus cos phi gamma 1 of s sin phi naught, the second component ds, and what you have to notice is that this cos phi naught sin phi naught are constants, okay. And the other thing that you have to notice is that this is actually this term here is actually rotation by the angle phi naught of cos phi gamma 1 s sin phi gamma 1 of s. So that is the interesting thing that you have to notice. So this is actually integral s naught to s, okay, of I will write it like this, rotation matrix given by the angle phi naught, which is going to be cos phi naught sin phi naught minus sin phi naught cos phi naught, acting on this vector, you see, cos phi 1 phi gamma 1 of s sin phi gamma 1 of s ds. Okay, if you expand it out, you see this is what you will get. First row into first column will give you the first component, okay, and second row into this first column will give you the second component, right. And notice that this is a constant matrix. It is actually rotation by the angle phi naught, okay. So it can be pulled out of the integration. So this is just if I call this as r phi naught, the rotation by phi naught. So I will get r phi naught acting on integral s naught to s. What I will be left with inside is cos phi gamma 1 s comma sin phi gamma 1 of s ds, okay. But what is this? This is exactly gamma 1 dot, because phi gamma 1 s is a turning angle for gamma 1 dot. So this is actually r phi naught integral s naught to s gamma 1 dot of s ds, which by the fundamental theorem of calculus is r phi naught gamma 1 of s minus gamma 1 of s naught, okay. So on the left side you see I had gamma 2 s minus gamma 2 s naught. So let me write it here, gamma 2 s minus gamma 2 s naught. So you are getting from this, what you are getting is that gamma 2 s is r phi naught gamma 1 of s, okay, minus r phi naught acting on gamma 1 of s naught, okay. Mind you, r sub phi naught is a linear map, so it will for a linear map f of x plus y is fx plus fy. So I can remove this term, I can put the minus outside, okay. So r phi naught of x plus y is r phi naught of x plus r phi naught of y, alright, because r phi naught is linear, and then there is this minus gamma to s naught that goes to the other side. So I will get a plus gamma to s naught. So basically you are getting gamma 2 is equal to r phi naught of gamma 1 of s plus some v naught, some vector v naught, alright. And what have you proved? You have proved that gamma 2 of s is you take gamma 1 of s, apply a rotation, then translate by v naught. Therefore gamma 2 of s is gotten by taking gamma 1 of s and applying a rigid motion. And what you have to understand is that this rotation is a orientation preserving rotation. That you can check that by noting that the matrix of this rotation has determinant plus 1, okay. So it any rotation for that matter will be determinant preserving, I mean it will be orientation preserving, okay, except that if the if the angle is negative, then it will become a clockwise rotation. If the angle is positive, it will be an anti-clockwise rotation, okay. So therefore moral of the story is, if we set m to be r phi naught plus v naught, okay. So m of v, if you want, let me write it like that, mv is equal to r phi naught v plus v naught, then m is a rigid motion of R2 such that gamma 2 is m circle gamma 1, okay. So therefore what we have proved is that if two curves have the same curvature, then there is a rigid motion that moves one to the other. Of course if we have proved m moves gamma 1 to gamma 2, then M inverse will move gamma 2 to gamma 1. Okay. So if two curves have the same curvatures, sine curvatures, then they are rigid motion equivalent. Okay. So the only final statement that we need to prove is that you give me an arbitrary continuous function, I can find a curve for which that continuous function is the sine curvature. That is the only thing that is left. And once you do that, what you get is you get a bijective correspondence between rigid motion equivalence classes of curves on one side and continuous functions which represent the sine curvatures on the other side. And this one-to-one correspondence confirms and gives a precise mathematical meaning to the statement that plane curve is completely controlled up to rigid motions by its sine curvature. Okay. So let us prove the last thing. Finally, let us take capital phi of s in C naught AB. So it is a continuous function on AB, alright. We will find a curve, unit speed parameterized curve for which the sine curvature is capital phi. We will find a unit speed parameterized curve gamma equal to gamma of s belonging to AB such that the sine curvature of gamma is actually phi. Okay. So again the way to go is that if there is such a curve, then it is unit speed, then the tangent vector has a turning angle and the rate of change of the turning angle is the curvature, and the curvature function is supposed to be phi that is given. So the rate of change of the turning angle is given as phi. Therefore the turning angle can be obtained by integration, and then you can plug that turning angle into cos theta sin theta to get your curve, and you can verify that curve fits the bill. Okay. So it is quite straightforward. So the essential use of the turning angle is being made, alright. So notice that if such a gamma exists, then gamma dot has a turning angle whose derivative is Ps, is phi. So define phi of s minus phi of s naught to be integral s naught to s d phi of s. So I'll I'll put it in quotes, so I'll write it like this. Okay. So you see at the back of your mind, you want to find gamma such that ks gamma is phi. Okay. But then this ks gamma is actually d small phi by ds. Okay. So there is a turning angle phi sub gamma of s whose derivative d phi sub gamma of s by ds is your phi. So d phi by ds is phi. So you write integral phi to be small phi. Okay, that should be the turning angle. So you define phi like this. Okay, mind you, phi is continuous and the integral of a continuous function exists. Okay, and the derivative of the integral is again the original function. Therefore when you take the integral, it's going to be derivable and its derivative is a given function which is continuous. So that means the integral is actually C1. Okay. So notice that phi is C1, phi is in C1 AB, okay, all right, because its derivative since d phi by ds is capital phi, by the fundamental theorem of calculus, all right, and capital phi is in C naught, okay, and so phi is in C1, and what you will have is that consider gamma of S to be defined like this, cos phi of S comma sin phi of S, okay. So okay, so let me write it like this, cos, consider yeah, so again at the back of your mind you see, if there is a gamma for which the sine curvature is capital phi, okay, then gamma dot has the turning angle phi sub small phi sub gamma. So you have to take gamma dot, so you have to consider gamma dot to be cos phi s sin phi s, okay, and therefore to get gamma from gamma dot you have to integrate gamma, okay, and every time you integrate you see you get one more level of continuous differentiability. So you see original phi was C naught, integrating that you get small phi, and that is C1, okay, and now you see this cos small phi and sin small phi, they are again C1, and that is capital gamma dot. You integrate that you will get capital gamma, and gamma will now be C2, okay. So you see, consider this is equal to this, define, so you integrate it, so you define gamma s minus gamma of s naught to be integral from s naught to s naught to s, gamma dot of s, okay, ds, okay, and this is going to be of course integral from s naught to s, cos phi s comma sin phi s ds, okay. Then so the net effect of this is that then your gamma is in C2AB, it is twice continuously differentiable, because the derivative, because d gamma by ds will be gamma dot, and gamma dot is given by cos phi s sin phi s, and mind you phi is C1 and cos and sin are actually analytic, they are infinitely differentiable, therefore the composition cos phi s and sin phi s are also C1, so this whole thing is C1, so the gamma dot is in C1 AB, okay, and so derivative of gamma is in C1, that means gamma is in C2, okay. So gamma is C2, and by definition norm gamma dot is 1, and norm gamma dot is actually 1 because gamma dot is just cos theta sin theta, so it is a unit speed curve, okay, and by definition the sine curvature of gamma is exactly phi, okay, and k sine gamma of s is d phi sub gamma of s by ds, okay, and which is so I should say something here. I just want to say that so d phi sub gamma of s by ds is the same as d phi s by ds, okay, and this is equal to k sub s gamma of s, I mean is equal to capital phi, okay, and why are these two the same? You see, your gamma, the way the gamma is defined, it is a unit speed curve, so it will also have a it is so its derivative is a gamma dot will be C1 unit vector, so it will have a turning angle. When we showed the existence of turning angle, we showed that any two turning angles will differ only by a constant, okay. So if any two turning angles have the same value at some point, then they will be throughout equal, okay. The turning angle the initial value of the turning angle, which is the phase, that is the only difference that can that you can have between two turning angles, right. Therefore, moral of the story is that you see the turning angles two turning angles differ by a constant. And therefore, you get the sign curvature of gamma to be phi. Okay, so we have finally been able to get the proof. So what we have proved is a classification theorem. So we get the classification theorem for plane curves. Namely, on the left side you take gamma is equal to gamma of s, gamma so s is in AB, gamma unit speed, okay, and then you go modulo this equivalence relation. So this is the equivalence by rigid motions of R2. Okay, so this set on the left side is the set of rigid motion equivalence classes. Okay, and any member here is written as square bracket gamma, where the square bracket of gamma is supposed to include all rigid motion equivalent curves which are rigid motion equivalent to gamma. So this square bracket gamma is actually the set of all m circle gamma, where m is a rigid motion. Okay, you put all the rigid motions of a curve in one equivalence class. Okay, and one curve being rigid motion equivalent to the other is an equivalence relation. Every curve is rigid motion equivalent to it itself by the identity map, which is a rigid motion. And if one curve can be moved to another curve by rigid motion, then the second curve can be moved back to the first curve by the inverse of a rigid motion, because the inverse of a rigid motion is also a rigid motion, and that is symmetry. And for transitivity, if a first curve can be moved by rigid motion to a second curve, and the second curve can be moved by yet another rigid motion to the third curve, okay, then the composition of two rigid motions will move the first curve directly to the third curve, and the composition of two rigid motions is also a rigid motion. The fact is that all the rigid motions form a group, okay, and so this group is acting on all curves, and these equivalence classes are exactly the orbits of the action, as it is called in mathematics. Okay, so these are so what is happening is that these equivalence classes are there, and you have this map from this to C0AB, and the map is you send any rigid motion equivalence class of curves to the corresponding sign curvature. Okay, and what we have proved is that this map is bijective, and that is the classification theorem for plane curves. Okay, so there's one thing that I wanted to say, that somewhere I mentioned that when you take a rigid motion of R2, you can break it down into translation, and what is left will actually be a harnessed rotation. Okay, and in other words, I am saying that if you take a rigid motion which fixes the origin in R2, then it has to be a rotation. Okay, so that is this fact. Okay, and I would like to just explain what is the how to see that geometrically. Okay, so you see, you have is a remark, a rigid motion a rigid motion of R2 which fixes the origin is necessarily a rotation r theta, which is going to be given by cos theta sin theta minus sin theta cos theta. Okay, it is necessarily a rotation. Okay, so I should say a rigid motion here. Okay, and how do you see this? So you see so you have a situation like this. You have R2 and you have this, I will call this as M, it is going from R2 to R2, okay, and you see origin is going back to the origin, alright. See this rigid motion which fixes the origin, see the moment an isometry takes the origin to the origin, it is linear, we already know that, and rigid motions are certainly isometries. So if a rigid motion fixes the origin, then it is going to be a linear map. So it is going to be a linear map from R2 to R2, okay, and remember that so it is going to be a linear isometry, and you know a linear isometry will preserve norms, it will preserve dot products, okay, and because it is a rigid motion, it will be oriented. So it will be a linear map which preserves dot products, it preserves norms, it preserves angles between vectors, it preserves lengths of vectors, and it also preserves the sense in which the angles are measured between the vectors, okay, and I claim that such a map has to be a rotation, okay. Now what is special about a rotation? A rotation, if it is not the identity, the one thing that you can notice is that it has to move everything except the origin, okay. You take any line through the origin, okay, if the rotation is not the identity map, okay, then it has to move the line. Though there is only one case when it is rotation by 90 degrees, I mean if it is rotation by 180 degrees, then the line will go back to that line, okay. And if you leave out this case when you know the rotation is not rotation by 180 degrees, it has to move every line through the origin to some other line which is not the same line, okay. So you see, first you have to show that such a map, okay, it is going to move every line through the origin, okay, and then conclude from that it is a rotation, alright. Now how do you show that it moves every line through the origin to some other line through the origin? Of course you take a line through the origin, that is a subspace, and this is a linear map will take a subspace to a subspace, and in fact this is a linear isomorphism, mind you, linear isometries are linear isomorphisms because they are invertible, that is because of the rank nullity theorem, alright. Therefore you see any line through the origin will be mapped by the by the linear isometry to another map to another line through the origin. So you have to only rule out the case that a line is not mapped to itself, okay. But when a line is mapped by a linear map to itself, it means that there is an eigenvector on that line, okay. So there is every vector on the line, okay, is being mapped to some scalar times that same vector, and that if that scalar is positive, then it is in the same direction of the line, okay, from the origin, and if the scalar is negative, it is in the opposite direction on the same line from the origin, okay. So what you have to show is that a map like this, okay, except for the case when the rotation is by 180 degrees, okay, in which case the line is mapped back to itself, but every vector on the line is rotated by 180 degrees. Except for that case, alright, in every other case it is moving a line to some other line, not back to itself. So you have to rule out the situation that there are no eigenvectors, okay. So what is an eigenvector? It is a vector which is taken by the map to a scalar of itself, scalar multiple of itself, and that scalar multiple is called the eigenvalue, okay. So you have to rule out so look at this situation. Suppose I have a line L, okay, and suppose G takes, so let me write it like this. L is GL, suppose. So of course I have written G. The truth is that M is G, because here M is, see, this M is, if you break it down, it is actually translation by M0, circle G sub M, okay, but this M0 is 0. So this translation by 0 is identity. So this is just G sub M, which I would like to call as G, okay. So this, suppose L is moved to itself by G, okay, then this means, you know, G of V naught. So if I take a V naught here, you know, vector here on the line, G V naught should be lambda V naught. This should happen, okay, and see, this will happen if and only if, you know, lambda is an eigenvalue with, you know, eigenvector V naught, okay. So for people who do linear algebra, you know, you have this kind of analysis by using eigenvectors and eigenvalues, okay. Eigenen in German means self, okay. So eigenvector is a self vector, that means a vector that the linear map maps to a scalar of itself. So V naught is going to scalar times V naught, and that scalar that is involved is called the eigenvalue, okay. And you see, if this happens, see, this is the only case when the line is going to go to itself, okay. And to say that G is a rotation, I have to rule this out, okay, except for the case when it is rotation by 180 degrees. But that case when it is rotation by 180 degrees is very funny. So you see, I want to first rule out the you know, this case when a line is going back to itself, right. If it does, what happens? You see, you get this eigenvector eigenvalue, okay, but now use the fact that G is an isometry. So you see, norm G V naught is norm V naught, that's because V is an isometry. So you apply it, this will tell you that you will get norm lambda V naught is equal to norm V naught, okay, you will get this, okay. And then but you see, norm lambda V naught is mod lambda norm V naught. So this will tell you that mod lambda norm V naught is equal to norm V naught, okay. And V naught being a non-zero vector, I can cancel this, okay. And what I mean by that is, therefore mod lambda is 1. So in other words, you see, mod lambda is 1, okay. And so you see, if lambda is a real number, okay, then lambda can be only plus or minus 1. If lambda is a real number, then, you know, lambda is plus or minus 1, all right. Now you know, the truth is that you know, lambda will not be real, okay, because this G is going to be a rotation matrix. G is going to be r theta, and for r theta, look at the matrix, it's cos theta, sin theta, minus sin theta, cos theta, okay. You will, if you look at the eigenvalues of this matrix, if you write the characteristic polynomial, okay, you will see that you will get a quadratic equation which has only imaginary eigenvalues, okay. Therefore the truth is that, you know, you will not have any real eigenvalues at all. That is what shows that it is a rotation. So lambda, this G being isometry, will tell you that this lambda eigenvalue can only be plus or minus 1. But imagine if lambda is plus 1, okay, then G will become identity. So let me write the following thing. See, if lambda is plus 1, okay, then what happens is that, you see, G then G fixes that line, then G fixes L pointwise, okay. See, since, you know, G of lambda V, so G lambda V naught, so let me, instead of lambda, let me put a mu. See, G mu V naught is mu G V naught is equal to V naught, mu V naught, because G V naught is V naught. So every vector on that line will be fixed. That means the whole line will be fixed by G, okay, the whole line will be fixed by G, okay. And now look at this. You see, I want to now say that this is not possible. And why is that true? I mean, this is not possible unless G is the identity. All right. So I want to say, so you see, you have this situation. So if you think about it, see, you have this line that is pointwise fixed by, you take any mu v naught, then this is also G of mu v naught. Okay, and so this so if I take a unit vector along that line, okay, and if I take a perpendicular unit vector to that unit vector, which is gotten by rotating by 90 degrees in the anticlockwise sense, okay, and you apply G to it, okay, what will happen is that, you see, G being orthogonal, okay, it will take the perpendicular unit vector to a perpendicular unit vector, but it should also be being oriented, it should also preserve the sense. So what it will do is that G will fix another line perpendicular to it, okay, and the moment a linear map fixes two linearly independent vectors, it's the identity, that's all, okay. And that is because every vector can be broken down as uniquely as a linear combination of two linearly independent vectors, and if G fixes two linearly independent vectors, if a linear map fixes two linearly independent vectors, okay, it's actually fixing a basis, so it has to be the identity, okay. So therefore this case G has to be the identity, there is no possibility, okay. So you see, so let me write it like this. I have here, I have V naught cap, okay, and if you take this W naught cap, which is obtained from V naught cap by rotating by 90 degrees, okay, then you see, so V naught cap is equal to V naught by norm V naught, okay, and W naught cap is equal to a unit vector obtained by rotating V naught cap anti-clockwise by 90 degrees, okay. Then G of W naught cap, okay, notice that since G is an isometry, G W naught cap will also be unit vector, and since G is oriented, G W naught cap should be gotten from G V naught cap by rotating by 90 degrees, but G V naught cap is just V naught cap, so therefore G W naught cap is just simply W naught cap, okay. So okay, and this implies that this line through so this line L perpendicular, which is line perpendicular to L, that is also fixed by G. And this implies that G is the identity map, okay. So the moral of the story is that if it is not the identity map, okay, then this lambda equal to +1 eigenvalue will not get, all right, or if you insist on lambda equal to +1 eigenvalue, it has to only be the identity map, there is no other choice, okay. So so if G is not the identity map, then lambda equal to +1 is not an eigenvalue, okay. And it means, what does it mean? That so there is one more case when lambda is -1, okay, and if lambda is -1, okay, then the same kind of argument, okay, will tell you that basically what will happen is V naught will go to -V naught, and W naught will go to -W naught, and you can see that there is what is happening is a complete rotation by 180 degrees, okay. So So I want to say that if lambda equal to minus 1, then we can see that G is rotation by 180 degrees, right? And of course, if you put I mean in this rotation matrix, if you put theta equal to pi, and that is 180 degree rotation, right? So that case is there, all right. So these are the only two cases, okay. And so therefore the only cases where you can get these eigenvalues are either the identity map, which you can think of as rotation by 0 degrees, okay, or you will get rotation by 180 degrees, okay. And if it is none of these, okay, then there are no real eigenvalues, they are complex eigenvalues, okay. And in that case also, you see, again by so if there are no real eigenvalues, it means no line is fixed, no line through the origin is fixed. So every you take any vector along a line through the origin, it will go to some other vector, it will be rotation by some angle, okay. Now if you take some other vector, okay, and take the rotation of that, then the angles between these two original vectors and their rotated vectors should be preserved, and that will tell you that the all the vectors are rotated by the same angle that any single vector is rotated by. Therefore it is again a rotation by an angle theta. Therefore in all cases this is only a rotation, okay. And there are two special cases when the rotation is by 0 degrees, it is the identity map eigenvalue 1. When the rotation is by 180 degrees, it is eigenvalue minus 1. In all other cases, it is complex eigenvalues and it is rotation by an angle theta, which is different from 0 or 180, okay. So in all cases, this is always a linear oriented isometry of R2 is only a rotation, okay. Now the same kind of analysis can also be done in R3, okay, and you can show that you will get rotation about an axis passing through the origin, okay. You can make these kind of analysis. You are asking why translation is needed. That's because the general rigid motion is not necessarily linear. That is the problem. See, even in what is the problem? The problem is when you make a rigid motion, okay, it may move the origin to some other point, and if it moves the origin to a point different from the origin, it has it is failing in linearity only in that aspect. So what you do is that if you break the part, if you break the whole rigid motion into two pieces, one part being moving the origin to some other point, and then you start considering rotations about that point, then you can break the any rigid motion into a translation and rotation in that sense. But a general rigid motion is not linear, that is the problem, because a linear map has to take 0 to 0, okay, and a general rigid motion can move the origin. A general rigid motion can move the origin, and therefore this translation part has to be taken care of. So that is the reason what you do is that if you give me a rigid motion, okay, origin goes to some other point, it is not linear. What you do is that you again move that point back to the origin by a translation, okay, and you look at the composition. The composition becomes a rigid motion that takes origin to the origin, and therefore that becomes linear, okay. So this translation cannot be, you cannot forget it. Translation is important, but what happens is that when you take gamma dot, okay, the translation part disappears, because your the translation part involves adding a constant vector to gamma, and when you apply d by ds, that constant goes away. So basically some curve with a Frenet-Serret frame, you translate it, you will get a new curve with the same Frenet-Serret frame. Literally, the translation is not going to disturb the Frenet-Serret frame. It's only the rotation part of the rigid motion that is going to twist the Frenet-Serret frame. Okay, but the translation has to be included. Okay, so yeah, so I think I will stop here, right? So I want you to just let me write one last line here. If lambda is not equal to plus or minus 1, then G has complex eigenvalues and is again seen to be a rotation. Okay. So in any case, it's only a rotation, and I want to say that in the lambda equal to plus 1 case, G is identity of R2, and this is rotation by 0. Okay. This is rotation by 0. So in all cases, it's a rotation, right? So I'll stop here. Okay. So we have kind of done this classification thing properly. What I'm going to do next is I have to do I have to tell you something about involutes, evolutes, okay, and parallel curves. Then I have to tell you something about the 4 vertex theorem, and also about the isoperimetric inequality. These are all global theorems about curves. Okay, so I will stop here.